afternoon, everybody. Thank you for staying with us for an exciting panel about quantum technologies. Thanks to my fellow panelists here. So I'm going to start introducing myself, then we'll jump into tough questions. As you'll see, so I'm Christophe Jurczak. I'm a managing partner at a fund, venture capital fund that's called Quantonation. I'm a physicist by training. Actually, I did my PhD a long time ago with Anand, who turned out to get the Nobel Prize in 2022. My fund has invested in 32 companies, which makes us by far the largest investor in that field. I think Rick asked me earlier, how do I make money? We can get into it probably a little bit later. But pretty excited. I started in 2018, and then there was a lot of skepticism about the field. I think, it was warranted, to be honest. Now, the thing that is really amazing is that people are starting to ask, what can I do with these machines? What are they good for? And not just, will it ever happen? So in this panel, we'll cover a couple of questions, trying to focus on the applications of these technologies. And I hope you'll learn also from that, what to do, not to miss the revolution that is ongoing in front of us. So maybe I'll start with a simple question for my panelists. Please introduce yourselves and maybe just tell the audience a few facts about the quantum sector or quantum technologies that you would like to share. What matters to you? Why is it important? Maybe Rick, we can start. Nick, sorry. Nick.
Sure, I can start. So my name's Nicholas Rubin. I work at Google Quantum AI. I'm on the algorithms team. My background is I've spent about 10 years in quantum information at this point, and prior to that I was in quantum chemistry. Not quite an elder statesman of quantum information, but certainly getting there. So one thing that I think that everyone should take away, or it would be great if everyone took away from this panel about quantum information, is really that when you read about quantum computing in the news, you're really sort of seeing two modalities of computation. One of those is analog, and the other is digital. And there's really only one of those where you get an exponential improvement or a provable exponential improvement in computational speed. And so that's the digital side. And when we think about investing in building one of these devices and supporting researchers in this area, we need to rely on theoretical, proven exponential speedups. And so on the digital side, that means implementing something called fault-tolerant quantum computing, which is effectively allowing qubits to operate at very low error rate. And so that's sort of the main takeaway, if I had to pick one thing for people to remember, is that if you want exponential speedups with quantum computing, you're going to have to implement quantum error correction.
Thanks. Anand, some thoughts?
Hi, everyone. My name is Anand. I lead strategic partnerships at Quantinuum, which is where we work very closely with our industry partners on a lot of the applications that they're interested in and figuring out exactly where quantum computing will be applied within their business. My background is in computational materials science. And for those of you who don't know Quantinuum, we're the world's largest quantum computing company, majority owned by Honeywell. I guess, Christophe, to answer your question of what would be a good takeaway for people to remember about quantum computing, I think a lot of people ask, will quantum computing solve big data problems? And the answer is a definite no. Where quantum computing really fits in is where you have really hard compute problems. Often these are data light, if you want to think of it that way. And I think that's a good framework to remember as you start to figure out which of your applications could be amenable to being solved by a quantum computer.
Thank you, Anand. But there's not only quantum computing, so we started with that, and most of the panel will be focusing on quantum computing, actually. There's quite a bit to say about that. But Rick, maybe you can enlighten us a little bit about other applications as well.
Sure. I'm Rick Muller. I'm the director of the Intelligence Advanced Research Projects Activity, IARPA. Before coming to IARPA, I spent 20 years at San Diego National Laboratories, so I know the DOE space and the National Laboratory and ARPA-E well. So in addition to being able to do computation, quantum computers also have advantages in sensing and communication. And the same kind of information density that makes quantum computing possible also makes improved sensing possible. So we can do things like very accurate positional sensing or very accurate sensing of electric or magnetic fields using different types of quantum sensors. And similarly, you can do communications and networking capabilities that make use of, again, superpositions and entanglements, two of the kind of physical effects that quantum information science makes use of. And you can mix these things together. So I think some of the really interesting areas in the future could be to combine networking capabilities with computation. So you can do distributed quantum computation or combine that with sensing capabilities. So you could do distributed sensing and maybe compute on a distributedly sensed signal. So you can combine all three of those capabilities together. And I think one of the things we are seeing now is a real flourishing of the devices that make quantum information processing possible. And as those technologies mature, I think we're going to have the opportunity to look at some of these other application areas as well.
Yeah. There's an important angle, maybe, Rick, you can touch on a little bit, is about post-quantum crypto, cybersecurity angle with quantum computing. Can you say a few words about that?
Yeah, so, one of the first applications, let me back up even further. So we think quantum computers, we know quantum computers can do two things very well. They might be able to do a lot of things well, but essentially Shor's algorithm showed that quantum computers could factor integers in a way that puts at risk a lot of our cryptography that we use to protect our own secrets. And then the other application, you'll notice that there are a lot of computational chemists and material scientists here. We think quantum computers can also simulate other quantum systems. But on that first one, there's the risk that if we get a quantum computer, it might enable malicious people to crack, internet security and passwords and things like that. So around 10 years ago now, the National Institutes of Standards and Technology, NIST, started an effort on post-quantum cryptography. And the way cryptosystems work is you typically need many people looking at them to make sure that they're secure. So that's why they developed a number of candidates 10 years ago and put out calls for people to invent their own systems. And it looks like they've got 4 really solid candidates for various crypto systems right now. So I think we all own a debt of gratitude to NIST for having developed those capabilities.
Yeah. And I think it's fair to say as well, many energy companies in particular will have to transition to post-quantum crypto over the next couple of years. Maybe not so much a focus for this panel, but to keep in mind. Something I forgot to mention is actually that I've spent also myself 15 years in the renewable energy space, actually, government, IEA, at an IPP in California as well. And it was really a pleasure to be down at the exhibit and see all these companies, academic institutions as well. And I was looking at people working on grid balancing, sensors for nuclear systems, magnets, new magnets, trace gas sensors, new battery companies. And I felt like, ooh, there's a lot of applications for us here, things that my portfolio companies could work on. They should come next year and maybe engage with all these people. So maybe now we can jump into the applications of quantum computing, and we'll ask Nick in particular and Anand to focus maybe and tell us a little bit about applications in the energy sector that you have been working on that you think could be relevant for the audience.
Yeah, sure. So as Rick said, the sort of algorithmic idea that really started the field that gave us an idea that we would be able to get exponential speedups was Shor's algorithm and factoring. But even before that, it was proposed very naturally that if you want to simulate a quantum system with a classical computer, we know there's a very high cost computationally. And so you should make a computer out of a physical system to lower that cost. And so using a quantum computer to simulate nature is a very, very, very natural use case. And so one thing that we've been doing is looking for applications in that space relevant to the energy community. And 2 really have popped up that we have identified. One is naturally simulating the physics of batteries. All of these actually boil down to fundamental physics questions in chemistry or material science. And we can identify specifically which algorithms are going to run fastest and then price those out, imagining the devices that we're going to have closer to the end of the decade to determine the size of the computational speed up and whether there's actually value there. A second area that we've been looking at, which is a little bit more provocative, it sounds a little bit like hype, is looking at applications of simulation in fusion. So you sort of when marketing people hear the combination of quantum computing and fusion, it seems like too good to be true. But indeed, from a science perspective, there's actually a lot of simulation there's a lot of simulation needed in the fusion space. So we worked with Sandia National Laboratories on a specific application related to stopping power, or how heating works in the inertial confinement fusion setup, the ones that are run at the National Ignition Facility in Livermore. And it was very, very surprising to see that with a very modest size fault-tolerant quantum computer, you could execute computations that really do inform the design decisions necessary to achieve over-unity fusion there. And so that was a really exciting thing, and I think speaks to the fact that there are a lot of applications in this space.
Okay. Anand, maybe different sectors you could cover?
Yeah, sure. I'll just start with the chemistry and material science applications first, because those are at the core of the initial applications that we'll see a benefit from quantum computing. So we've been working with, for example, BMW and Airbus for a long time now, modeling catalytic reactions that take place within hydrogen fuel cells, and really drilling down to specific reactions like the oxygen reduction reaction, which are poorly treated with classical simulation techniques, all with the goal of eventually designing fuel cells that move away from the use of precious metals. So that's a key area. Again, in another catalytic example, we've been looking at the petrochemical industry and ammonia production, specifically the production of ammonia using iron-based catalysts, modeling those with Equinor, a Norwegian energy company. But I think now moving away from the materials and chemistry side, there are some interesting applications of quantum computing in solving differential equations more generally. And some of the applications there that we've been looking at have been around seismic modeling, for example, with BP, where we look at specifically the forward modeling problem, seeing what memory benefits can quantum computers provide for these seismic modeling problems, as well as computational fluid dynamics problems, which we've been looking at with the German Aerospace Center, DLR. And within the CFD subset, we've been specifically focused on cases where there's a ton of turbulence, where these are really hard to resolve with classical models, especially given the compute intensity that you need to resolve these models with high accuracy. So again, trying to understand what role do quantum computers and quantum algorithms have to play for these types of problems outside of the pure chemistry material science space.
Okay. So I know also of some applications in load balancing towards the grid. Obviously, it's also something that could be an interest. But maybe we're coming back to the material story, because we've got distinguished chemists, moreover, in the panel. So usually when I'm asking quantum computing startups what is their killer app, the first application, physicist founders in these startups, they tell me that's chemistry, because chemists don't know how to compute. You need a quantum computer to compute chemistry. Actually, it's not exactly true. I mean, especially DOE, you know, they're running very big simulations. You can model pretty large molecules already. So my question to you, both Nick and Rick, actually, is, what is different with quantum? What does it bring? Since we know already how to model these molecules, to do maybe approximate simulations, where can we go with quantum? And why does it change the rules of the game a little bit?
So Christophe, you're absolutely right in that there are really great approximate methods for molecules and materials that quantum chemists and computational chemists have been building over the last 60 years or so. One of the things that those methods don't give you is a systematic way of correcting those approximations. And typically, once you start building in the ability to make the calculation a little bit better and make the calculation a little bit better, you get into these realms of what we call exponentially scaling problems, which simply means that they get more expensive than you can build computers to catch up to. So one of the things that a quantum computer gives you is not only the ability to compute, let's say, a potential energy surface for a chemical reaction that you're interested in, but then to start putting error bounds on those to give you some level of assurance as to how accurately you know those parameters. And so I'll hand it off to Nick for.
Yeah, I have the same view because I think we've probably both been working in quantum chemistry for a really long time, and we know that there's a huge asterisk on the statement that quantum computers are going to be helpful for chemistry. It's not like we are not able to compute things right now. It's just a question of accuracy. And so even for these examples that we were talking about before, the DOE is already designing fusion reactors with classical computation. It's very difficult to engineer experimental conditions if your experiments are at temperatures and pressures on the way to the sun. And so you have to address that with classical computation in some way. It's just a question of, does that actually feed back into any engineering decision you're going to be making later down the road? And the answer is that the data that we have is very sparse for a lot of chemistry and materials simulations. It would go much, much faster if we can have better approximations and better computational tools. And then ultimately, we need to be able to have some type of guarantee. And that's the comparison with the experiment at the end of the day. And so there is a big asterisk on, yes, of course, we are able to simulate nature at some accuracy right now. But the question is that useful for engineering practices? And I don't think we're quite there yet.
Well, and maybe something that was implicit in what you said that I'd like to underscore a little bit is that it's particularly at those extremes of temperature and pressure that our approximations break down. When we're doing room temperature, normal chemistry, we think those approximations work really well. When you're doing things like fusion reactions, one of the real challenges is understanding where those approximations start to fall apart. And we don't do a lot of chemistry at temperature of the sun type conditions. And therefore, we haven't tested those approximations to the same degree that we've tested our kind of room temperature standard, chemistry lab chemistry.
Yeah, so there must be a need also because ARPA-E launched a very cool program named QC3 on quantum computing for groundbreaking chemistry and materials science simulation. So we look forward, obviously, to the result, the outcome within a couple of years. So maybe many of you have seen pictures of quantum computers. Looks like nothing actually. A big, maybe you guys have different configurations of machines, but what I want to touch upon is maybe, so we've been talking about, in the press, people are talking about the quantum advantage when we will reach an advantage with these machines. So in particular, we're thinking in terms of time to solution, which is one thing. Are there other things to think about the size of a machine? So I was mentioning DOE machine, maybe Aurora in Chicago. How does it compare to a machine like that? I mean, in terms of size, in terms of energy consumption, maybe as well. Can you say a few words about that, maybe with different configurations of typologies of qubits here?
Yeah, sure. So I think energy consumption is increasingly becoming a metric that people are tracking. Whether you want to call it for a quantum advantage or something similar. One of the experiments that we ran, recreating a Google experiment, random circuit sampling, it's a very theoretical experiment, nothing of practical use, but it does give an indication of how powerful your quantum computer is and whether you're able to do something that's beyond classical simulation. So we ran that experiment on our latest generation machine, and we were able to compare it against the power consumption that we thought a machine like Frontier would take. And we calculated that our machine took about 0.2 kilowatt hours for that experiment, and a machine like Frontier would actually take about 6,000 kilowatt hours to run that same exact simulation. And so already we're seeing about a 30,000 times power reduction, obviously on a contrived experiment, but these are metrics that are going to be important to continue tracking.
I think I would probably take this question in maybe something that's useful for the audience in terms of how do you define the boundary between what is classically accessible from a computational perspective, and what is something that you'll really need to use some other type of computing device, so beyond classical in some notion. And I'm particularly interested in how you define this boundary, how do you define problems that are on either side of these things, and we actually have a term internally that we use for a lot of the calculations that have been run today on quantum computers, where people claim that they make some type of physics discovery or some other type of beyond classical or utility scale thing. And that term is discoverinos. There's really nothing that has been run today that we couldn't simulate beyond these experiments where they're sort of very esoteric math problems like random circuit sampling. And really one sort of very clear boundary for tracking whether quantum computing is going to be useful from an applications perspective is if you can make discoveries through computation that are really inaccessible by classical. And so there you'll really have to check for the largest devices like Frontier at Oak Ridge, is this truly out of reach for that type of computational resource or not? And so that's something where we really judge the progress of the field.
Yeah, I think that's super important. That's something I've seen with startups as well, like the question of benchmarks, and really having subject matter experts in the companies who know what is to be beaten, actually, because you can make a lot of claims in quantum, but ultimately, classical computing works really well for optimization, for example, solvers, etc. So it's hard to beat, but we're getting there, and there's progress also on the benchmark side. So now I think, so moving on into something very practical, let's say. So assume I'm an attendee here, I'm intrigued, thinking about, might be good, might be useful, maybe can beat my competitors within a couple of years if I'm better and I'm using these quantum machines. So how do they do it, actually? How does anybody with a problem, let's say a computational problem, get into quantum and see if he could eventually, maybe not just right now, but within a couple of years, get the benefit from that? How to approach the, let's say, porting of your problem into a quantum computer? Could be Google, could be Quantinuum, could be anybody else. Does he have to buy a machine? I think it's anywhere between 1 and 50 million, I guess. It takes a little bit of time, it's a bit expensive. Are there other ways to have access to these machines? So if you can give us, maybe the three of you, a little bit some practical consideration, advice also to companies, to people in the room who would like to learn and to get into quantum at some point. Maybe Rick.
So I think one of the, I think both Google and Quantinuum have cloud-based solutions, as do most of the quantum providers now. And that's really a kind of wonderful place to be in. When IARPA started in quantum, there were barely working quantum devices at all. And so now, only 15 or so years later, the fact that if you're interested in these things, you can, rather inexpensively get time on cloud computing resources, use open source software packages to map your problems onto systems, I think is just a huge victory that the field in general has made.
Yeah. And I counted, I think there are if I'm not wrong, there are 65 quantum computers in the world built or being commissioned at the time. So that starts to be sizable. Maybe, Nick?
Sure. So I think that companies or groups that are interested in identifying whether quantum computation is going to be useful for a computational advantage associated with the problem of interest you have, probably the best way to get into it is interact with experts first and really be able to articulate very clearly and concisely what a computational problem is in your field or domain that has some particular value. So one mode of not doing or doing this poorly would be coming to, for example, the algorithms team at Google and saying, oh, we have this AI model and it runs slowly. Can you help us? Well, I don't know, use TensorFlow better or something. And that's really what we've seen in terms of getting computational advantage is you really have to identify the core thing that you want to compute and then be open to changing the way that you are designing an algorithm for that particular task. So it is very rare that we see that you can directly take a classical algorithm and run a quantum version of it and get some type of computational advantage, you usually have to change your process quite a bit, and that just takes time. And this will give a lot of people insight into the types of problems, the formulation that they need to have, and sort of the parameter space that you need to get computational advantage, which ultimately is the only thing that matters.
Yeah. I think one thing that's important, I think, to understand as well is that maybe you will not transition, of course, all your computation to quantum. I think it's going to be a part of a complex workflow, and I'd be very happy if even in a, let's say, materials or a chemical discovery workflow, which is very complex, maybe 10% could transition to quantum. That would be a huge benefit for everybody getting to production for that. So it's not the whole workflow to change, but you have to identify the spots where it makes sense.
Yeah, I wanted to underscore both what you just said, Christophe, and something you said, Nick. So I think for a lot of problems, especially those outside of chemistry, material science applications, you do also need to think about how do you reformulate your problem or think of it in a different way, right, where quantum can be amenable to delivering those computational advantages. So again, just going back to that seismic modeling example, right, if you're trying to model your full wave field and read out the data from every single grid point in that wave field, you may lose any quantum speedup that you get because you have to perform measurements to read out at every single grid point. But if there's a way to reformulate that, maybe there are only particular points on your grid that you care about where your acoustic sensors are, then there may be a way to formulate that problem where you can retain those speedups. And then I think moving on to what you just said, Christophe, you do have to think of it as a full workflow, right? So we might be working on new algorithms for the forward modeling side of that seismic problem, but then how do you actually do a full waveform inversion? And how do you connect it to classical processing to perform maybe that inversion step? I think those are pieces that people haven't worked out yet and are going to be increasingly important, especially as you want to create real-world applications that combine the best of quantum and the best of classical processing.
Yeah. Okay, very clear. So one step further, now talking about the people, but the how to do it, really get into building a quantum workforce or integrate people with quantum knowledge. So you've seen all in the news over the last couple of months quite a lot of things. I mean, getting public with some impact on public stocks as well for quantum computing company, which has been pretty amazing and not completely irrational, I guess. But Google, Amazon, Microsoft, startups here and there have announced a lot of things. So there are roadmaps that are public as well. So for anybody who wants to get into quantum, I mean, what kind of resource workforce team do they need to build to decode that kind of information? There's a lot of hype, like with any new technology. It's been the case for, we mentioned fusion, but there are other things, obviously also fission for that matter. So quantum is not different. There's hype, but there's also tangible progress. So how to decode that and get really to transform that information into something useful for a company and ultimately, well, financial benefit at some point, obviously, maybe. Great.
Yeah, so, you know, I think one of the most exciting things about quantum computation for me is that it touches so many other fields of science. You know, often you need, you know, microwave engineers or optical engineers or mechanical engineers or computer programmers or, you know, quantum mechanics experts or algorithms experts. So I think one of the really gratifying parts of this has always been that when you're working on a team kind of building these quantum resources, you get to work with so many different experts in so many different areas. But that also means that if you're interested in getting into quantum information science, there are many entries into this. And so, you know, looking over the list I just went through, they're all fairly advanced technical fields. But, you know, computer programming is a great entry to any kind of advanced computational effort.
Any advice, Nick?
I would probably say that it is, if you want to work technically, then certainly there's a lot of, you need a lot of technical expertise. But if you just want to be able to evaluate where the field is to make some type of decision, whether you're participating or not, or to make some investment decision or something like that, there's sort of some key milestones that I think you can pay attention to. We know that if you want large computational speedups with any platform, whether it's superconducting qubits, photonics, ions, you're going to need to implement error correction. And there's some pretty key milestones along the way that these platforms all need to demonstrate. That's sort of a universal thing. And so you can look for those, and it doesn't require a PhD in quantum chemistry or physics. It just is, well, is this thing behaving the way that it should? And you can sift through the hype pretty easily to determine specifically, is this performing the functions that are being claimed? And so, yes, to participate at the level of technical advancement, it would require maybe an advanced degree. If you're just making a decision, I think there's some pretty clear yardstones, really, that you can see a decision being made.
And so in that field, we see a lot of POC, so proof of concept projects, being collaborations between customers and technology suppliers. Anand, maybe you can say a few words about that, how it helps also craft a strategy for a customer?
Yeah, absolutely. I think one of the things we've been talking about is how do you map your use cases, how do you find the right ones that are amenable for quantum computing. Assuming that you've done that, proof of concept is a good way to start. But I think when you think about those proof of concepts, it should guide what your future R&D investment or roadmap looks like for that specific business application. And the best way to do that is to figure out, okay, for this business application, what truly are the resources that I need or the performance that I need from quantum hardware, from quantum algorithms to unlock value. And I think getting very granular into those numerical details of the hardware and the algorithms is really important, because then you can tie those back to hardware roadmaps that we have published or Google has published or others, and say, okay, this is kind of the time frame that I know my business application will see some value. And then you can start to take steps to accelerate that timeline, right? You can identify where it is the improvements need to be made. Some of those will be improvements that need to be made by us quantum companies, but there may be things on the algorithm side, on the problem side, that you can specifically work on in parallel to building your quantum workforce that does accelerate that timeline.
Okay, thank you, very clear. And maybe last question. But so a question I'm asked often also as an investor. So everybody's talking about AI. We'll have a session tomorrow morning about that as well. So AI, quantum, should we choose? Should we do both? None? I mean, just a few words just to conclude maybe on that. How do you see some convergence people are talking about both technologies?
So I'll just point to one thing I think is really exciting, which is that John Preskill and other algorithm scientists have identified ways of learning a quantum signal, that there's a speed up in learning a quantum state from a quantum system. So if you're interested in doing sensing, you might be able to figure out what's been sensed much faster using a quantum computation, so quantum machine learning of quantum systems.
I think there is potential for combination, but you have to be, again, just like all of these other applications, very careful about how you combine both of those subjects.
Yeah, and I would say we're looking at the use of classical AI into every single layer of our technology stack, right? Whether that's better compilation, new quantum error correction codes that might again accelerate the timeline to value, and then on the flip side, how do you integrate this new type of data that these machines are generating now into classical AI pipelines?
Yeah, I think a key word for me in the end, so from the conversation, especially if you want to get into quantum, just look at your computational problems. I mean, like the ones that are really important for you, and get to talk to the experts to figure out which ones could be accelerated by quantum. Not everything will be accelerated. A fair share of the computational problems will be, and I think that's the way to approach that. It's not going to solve everything, but it's going to solve many of the problems, and we believe, I think, that many will be in the energy sector. So I hope, you've learned a couple of things here during this panel. I'd like to thank my panelists for this great discussion. Thank you.
Thank you.